And then you get the year installed.
She said she tried to find my email. She was trying to contact.
How are things with you?
Well, just like I think,
We're here.
no, not this year. Getting too old, man. The last
Pretty sure that's well, that's 16 inches. Plane was we were using the guaranteed so
there's a lot of material there.
So, yeah, they're actually guaranteed.
All right, everyone. All right, so welcome to June. It's our last meeting before September. Yeah, I know. My report's on the website, so you can read that. We have way too much time on your hands. Let's go straight to Bruce.
Currently, our member count stands at $10,815. PA count at $1,660. And we're doing pretty good. More money's coming in as usual. Everything's pretty nice. Better than a lot of other incentives are having to, fight for cash, so we're in a pretty good spot right now. We'll probably have some people talking about some big expenses coming in the future, but that's obviously for another time. We've already reserved the time for our annual general meeting at Noon Underwater, who actually won 2 silver medals for their brewing at the national championship. So something to think about, getting an extra bottle.
Have an extra glass.
That's on November 22nd, on Sunday. I've already figured out also the first night of getting back to RASCals at Cattle Point. That'll be on Friday, September 18th, near the Quarter Moon. So we'll be out there for that. And other than that, I'm pretty much just waiting for the bills to come in for the star party and the next public outreach flurry, and that's where we're at.
Great, thanks. Okay, Joy, do you have anything?
No, but the minutes have been approved through May and have been turned in, and I think they'll be posted soon.
Good, thanks. All right, Joe.
The website's running great.
If anyone has any questions, let me know. Also, if anyone is interested in contributing online articles, if you're a foreign blogger or if you just want to contribute, small articles are really worthwhile. Just be posted on the web. It's good. It's great for someone who wants to get involved in WordPress, see how it works. If you're interested in doing astronomy content or our website, please let me know.
Good, thanks, Joe. Chris?
Okay, current membership is 219.
Wow.
It actually went up during the council meeting last week. There's 11 people whose membership has lapsed in the either in April or May. So I'm in the process of taking over the email list for the center. So some of you may hear from me if I may be doing a few checks and things to see which email addresses to use. If I think a few people may have two on there, I'll spend some time this summer learning more about how that works.
Good, thanks, Chris.
Can I ask a question?
Yeah, go ahead.
Chris, is that the 11th, and you said the 11th has lapsed, and you like they're done and gone? Or
They're still part of the 200, they're counted in the 219. 5 of them are from April 30th, and if they don't renew by the end of this month, they will go.
Okay. And are we going to contact them?
That's what I was thinking. I don't think we've had a history of doing that, but I think, especially as some of these names are, a few of the names are familiar, so I think I probably will.
Malcolm, Sky News.
Sky News is at the front of the room, and always open for people that wish to contribute articles for it in the fall. Other than that, the current issue is available online as well as in print form. And this particular one has a nice color shot from Dog Dog. Thank you so much for the picture, John. And that's it.
Good, well done. Thanks, Malcolm. Just note on the Star Party, I haven't, I think we talked about renting the Chosen House for daytime things on Saturday afternoon, and we kind of didn't really make a decision. I decided not to, because now there's a surcharge to rent it. And unless there are 4 Chosen Community Association members in attendance at whatever event we hold in that house, then we get charged like an extra $20 surcharge, and the rates have gone up, and I don't feel like playing anymore, so we don't really have anything anyways. So I was thinking of asking maybe David or somebody just to do a couple of short talks in the afternoon in the little gazebo there, like his talk on the astronomy apps for phones, iPads, and stuff is really popular. That would probably go really nicely with the public, especially for a few public members that attend the Star Party would be interested in something like that. So I'm probably just going to ask a couple members to do short talks in the afternoon, and we'll just kind of concentrate on the evening things, because I don't feel like paying extra money for more and more each time. So other than that, the Star Parties, we just got to arrange the house and stuff, and we're good to go, and door prizes. All right, Sid, public outreach.
Outreach is almost over with the schools are closing. And Lori and I visited many schools this year. Also, there have been other public outreach events. Debrief, the last one was Debrief. Thanks to everyone who came, and thanks to other people who were not able to come. And next event is the Buccaneers Day this coming Saturday. If you are able to help, please let me know. We need some extra people. I have only 3 people so far. So if you could help, that would be wonderful. This Saturday from 11 to 3. So it's not too onerous. So before you go through the door, think about if you help. Buccaneers Day, Senate Strawberry Festival coming July 12th. potential symphony splash, and rest of our campsite, Senate Fair, these are the events coming. And I would like to thank Ken, who's going to be taking over the public outreach. Other than the schools, Ken Mallory, affected probably hobby show, yeah, perfect, that would be the big one. He has to retire, he has to quit his job because he loves so much public outreach, so he's quitting his job. Our total gallery of moments this year had, including Buccaneers Day, has been 6,801 to be precise. I did not click this clicker too much. In last council meeting, there was a question raised, what's the gallery of moments for the public at the DAO is? And it is 937 for 5 or 6 events we entertain the public. So thank you very, very much for everyone who helped. And if you could please help on June 13th and July 12th, that would be much appreciated. Yeah. Thank you.
Thanks, Ed. Thanks, Cam, for stepping up. Lori.
Well, just again, thanks to everybody who was involved in the DAO. The DAO nights, we had 6 really great nights all in a row. Stopped on the 30th of May, and then we'll be started back up again on July the 18th, and going for four straight nights, and then a little bit of a break as well. Then to August the 29th and September the 12th. And I've already got people phoning me about coming for the September 12th. And I'm going, oh no, we're going to have the same thing again. This last night is going to be really something. So we'll have to see. We'll have to see what we can do. I do have about 20, maybe 20 or so of these posters. But still, so if people would like, I just got them here, and if everybody would just take like one and put it up somewhere again, we'll just keep these going so that we can keep the interest up. I do have a sign on the gate. I guess how many did you say showed up on Saturday night?
Well, there's a full line of cards.
A full line of cards. Oh. So so it's that's just, it was to be kind of expected. So hopefully they didn't stay long.
No, they weren't angry. They're actually just
Okay.
they was there, so it's actually quite positive.
Okay, so we just please come under. Come on, 18th.
You didn't contact your sign on David.
Yes, right, yeah. Well, I mean, it's a big sign. How can we keep it anyway? But thanks
What's the sign
everybody.
say?
The sign says that the DAO summer star parties will resume or will be open on July the 18th.
Nice.
Yeah, so it was just, and we didn't want to, it was really hard because we couldn't phone CBC and the Times College and say, would you put something in the paper that says that we're not open? You know, I mean, that wouldn't work, you know, I mean, we would put something in for that. So it was kind of a little bit of a thing, but we had a few people. I'm sure every Saturday we'll probably have a few until people figure out that we're not open until they. If you are, I'm not going to be here for July, so Sherry is going to take over making sure that volunteers, so it would make her job really, really good if you could tell her well before the 18th and the 25th that you're going to, that you would mind going back up again and just, checking your name off, that she knows that you're coming up. So that would be great. Thank you.
Thanks, Lori.
Okay.
Okay, you want to talk about the website, Joe, so we'll just go to the tech committee for
Not a lot to report, really. Have a door prize for anyone who would like to take it off my hands. The old machine from the VCO, which was kindly donated at one point. It's a Pentium 4 of some variety. It runs Windows 7. And has a whole bunch of
showcase for us. This is great.
has all the necessary accessories and and comes with some astronomy software. As long as you don't reformat it. So anyone interested in that, please just go ahead and take it, really. If it's still there at the end of the night, I guess I'll take it back. Other than that, not really a lot to report this month.
Everything at the VCO going okay?
Yep.
Good.
And please come up. Get flown out there.
We got Friday?
Could do.
Anybody have anything else that they want to bring up? Chris?
I'm organizing a little event. It's an event I've been thinking about for years, but I actually only got off my craft and started working on it this week. July 14th is going to be a special day. It's going to be the day that New Horizons flies by Pluto. And I'm organizing a little celebration of that event at Pluto's restaurant. That evening, it's a Tuesday evening, and I contacted the owner this week. What I would like to do is, if you're interested in coming, let me know, so I can get some idea of how many people might show up. But the idea is mainly to have fun. I was hoping JJ Cavallars is going to be around, but apparently he's been pulled off by my dear friends at the CSA in Montreal. But he's given me a couple of names of people who might be able to. I was just thinking maybe kind of a very brief, like 5 or 10 minute talk about what's going on at that particular moment at Pluto. The actual moment that New Horizons goes by Pluto is about 4 in the morning on the 14th. Although that's kind of irrelevant because any signals take hours to come back. And I understand though that the first signals coming back from New Horizons is going to be spending most of that day gathering data rather than sending it back, understandably, because it's not going to be the flyby when it's quite close is not that long. It's traveling quite a clip. But about the time we sit down will be when we hear back from New Horizons about its health. So anyway, and I will be I'll send out an email to the membership about this and post some things on Facebook. But anyway, I just thought, we have Pluto's restaurant. It's been here for years. And this will be a great place. It's sort of, middle of the dead time for us. And I just thought it'd be a fun event. And we'll get together, maybe hear a little bit about what's going on. I may borrow the screen from the, if we have to, from the Astronomy Cafe or something, and we might be able to pick up NASA TV if there is something that day. So that's my little answer.
Daytime or?
We're talking I'd say about 6 p.m.
Okay.
6 p.m. Tuesday, July 14th.
Good question.
And, yes.
Is Pluto's restaurant now a minor restaurant?
They still have their liquor license from all out, from what I know. But actually, there's a terrific article just talking about New Horizons a little bit. There's a terrific article about sort of what's going to happen and when it happens. Going to happen in the July Sky Telescope. So I suggest that, and also the folks involved in New Horizons are going to do a show every week leading up to the flyby. And the first show appeared on YouTube and on their website today. I just watched it before I had dinner. Today is about a 20-minute show, but it's a nice little summary of what they've done and where they're at. Interviews with the principal investigators. It's quite interesting. And there are pictures coming down. They're still kind of fuzzy, and apparently the pictures aren't going to be really great until they get kind of close in, a couple of days before the flyby. But they're getting better. They're already now substantially better than the best pictures we had, which were from Hubble. So there is some action on that front, but they are kind of dressing it up as not saying this is to the minor planet, but this is what they call it. What is it? The third order of planets, or the third part of the solar system. You know, they have the small, the rocky inner planets and the big gas giants, and then this whole world out there of the dwarf planets and the Kuiper belt and all that sort of stuff. So this is actually an interesting thing. And another interesting slide, like just sorry for yakking so much. The July 14th is also the 50th anniversary of the first planetary flyby, when Mariner 4 went by Mars. So it's kind of an end of an era, though, because this is kind of the last of the classical planets. That was a line I picked up from that TV show. The last of the classical planets. We had all these flybys in the 80s and the 70s and the 60s, and this is the last one. So.
How do you find the videos? Just go YouTube and put in New Horizons.
Just go to YouTube and New Horizons Pluto, I would say, because New Horizons by itself could mean lots of things.
Thanks for organizing it. Oh, that sounds neat. Any other new business anyone wants to bring up? Okay, Lori, national issues?
Nothing really new from last week. We're off to Halifax, and we'll bring back some interesting things in September from what happened there, I hope. Yeah, I don't have anything new. Is there anything, Chris, that I am missing that I know that, I think I've already said that there'll be a little bit of an increase in the, in the $3-4 or something like that.
Yeah, and, Paul is stepping down from the board, so it's just going to be me. But our loss is Calgary's gain, because now Calgary is going to have 2 representatives on the board. Heather Laird was elected from there. And there should be some news coming out of this GA, including, I know that the executive is going to be changing around a little bit, but anyway.
Okay, thanks. Okay, so I see here we have Don from the Friends of the DAO. He's also one of our members too. So he's going to give us just a little kind of update on how things are progressing with their new society.
Yes, it is. As of June 5th, Friends of the DAO has been registered as a official society with the province of BC. And it's been a long road to get here. I think I stood here almost exactly a year ago talking about it. And what really made the difference is that Katrina Johnson and Ben Garman got involved, and they're a couple if you don't know them. And Ben got his PhD in astrophysics here at UVic back in 1990-91. And he was Governor General's Gold Medal winner for his PhD thesis. He went on to be lead programmer at Goddard Space Flight Center for the X-ray satellites, and he also did a number of other things. His work is actually still cited by many researchers in his field with in the ultraviolet range for stars. So he's a very impressive scientist, but he also has a passion for public education. And he and his wife both have experience in starting nonprofit associations. They took a volunteer association in the States and took it up to the point where it had paid staff. And this is what we're trying to do with the Friends of the DAO. And we have a very ambitious mandate. What we're trying to do here as a community organization, as many of you already know, is to try to restart the center of the universe in all its glory, and maybe even surpass it a little bit and try to improve on what was done. And that includes revitalizing the displays and maybe trying some new things. I think we have a little bit more flexibility as a community group rather than something contained within the National Research Council. So one of the first things we did was Ben and I came to the council meeting last week, and we asked for the RASC to become involved with this and to put forth 2 directors. I don't think that has been decided yet, but we think that this is a really key part of the success of this organization, because as you already know, you're already a big part of what goes on up there. The main part, 99.999% of it. So in any case, so we really want to have 2 representatives on board. And we also want everybody's input. You're all interested in this field, and we've actually set up an email address if you care to contact us with your ideas, and that's ideas@observatoryhill.org. So this could be thoughts of things that you've seen at science centers in Europe or the States, or just your thoughts on how we could be doing things better now, how maybe likes and dislikes from the center of the universe in the past, and so on. So please, this is, I guess they call this the blue sky part of the project. Maybe this is the dark sky or clear sky part of the project. But yes, this is the idea to really start dreaming about what we could do. So that's it.
Okay,
Good.
any questions for Don?
Is Friends of the DAO open for members of the public to join?
It will be very soon. We haven't decided on the date. Probably it's going to be like $10 or something like that. But yes, it will be open for membership. And this is intended as being more than just an astronomical group. We're not really an astronomical group as such. This is a community group that's representing its interests to the observatory. And so we're looking at getting people who are not in the astronomical community like all of you are, but instead maybe that still have an interest in place. So we're looking at grandparents and business owners and all sorts of people who would like to see the place from. Yeah.
So you don't want astronomers to do?
We absolutely do.
Oh,
we absolutely do. But it's not. We're not trying to duplicate anything we already see. Yeah.
Okay, thanks, Don.
Sherry, in that same regard, just by the 18th, will there be, will you have something up that says join up or sign up now?
Yes. Yes.
Okay, so
Yeah, that's maybe for.
Okay, all right, well then that's, because I was going to suggest, and we talked a little bit about this before, is putting up some sort of a donation box. Because that, but if you're doing that,
Well,
that will oversee.
Well, yeah, we have to think about that and how that relates to where we're going to see and where the donations are.
Yeah.
But there's a lot of questions and answers about that. Yes.
Okay.
A bit of a learning curve we had, how we sort of do the same thing in slightly different ways, or do different things in the same way, or how it's all going to kind of match, but
Yeah.
it'll come.
Yeah, I think part of the difficulty right now is with any communications to people don't necessarily hear what we want them to hear, and so we've already encountered that with some people thinking that the Saturday nights were run by the Friends of the DAO, which they're not. But you talk about the Friends of the DAO, they get that impression, so you have to be really careful about the messaging and so on. Yeah.
Anyone else? Okay, thanks, Don. So I guess I'll turn it over to Joe to introduce our evening's guest, which sounds like another great one. And this is our last meeting until September, so have a great summer, everybody. I don't know if you've been like me, but these last few nights have just been absolutely amazing. I haven't been to bed till 3 o'clock every morning since this is full moon. I'm getting up at 8, like I'm running about 5 hours. But I mean, these are the kind of nights we dream about all winter. Once you're outside in short sleeves, and the sky is wonderful, and it's just everything's warm and fuzzy. This is great. So let's hope we have a good summer, just like that for everybody. Okay, Joe?
If I missed anybody on the way, you need a calendar. There's some Canada Friends Hawaii calendars here, 2015.
Take a calendar, you get a break too.
So while our speaker sets up and figures out the high tech down here, Joel Brodiger is a research associate at NRC's Herzberg Astrophysics, and he's our speaker for tonight. His PhD was taken at Queen's University, and Slicing and Dicing Galaxies to Understand What Built Them Up is the title of the talk. Pretty catchy. When I went into his areas of interest, it was galaxy formation, stellar populations, galaxy structure, chemical evolution, environmental effects. Some of those are a trend, for sure. And he's sure going to tell us how it all fits together with his expertise in modeling, in particular, synthesis modeling. So, without further ado, Joel.
Thank you. So, although Joe named off quite a list of things that I'm interested in, I don't want to give you the impression that I actually do all those things. So thanks, Joe. It's great to be here tonight. Thank you for coming out and for inviting me to come speak to you. As Joe mentioned, my name is Joel Brodiger. I am a relatively recent addition to the core of postdocs at HIA. My main area of research, as you might have guessed, is in the formation of galaxies, specifically looking at galaxies around us in the nearby universe. And what I want to tell you about tonight is a somewhat new approach that is coming to the forefront within our field. And it's an approach that I'm taking up as well, which sees us analyzing galaxies on relatively small spatial scales, smaller than what we have normally approached galaxies on. And the idea there is, fundamentally, we want to understand the physics that happens on these particular scales, because we think that it plays a big role in the formation of the overall galactic systems that we see around us. And so the approach that I'm invoking in my work at HIA is actually taking galaxies like this one here, dicing them up into little bits, and looking at the stars within, say, individual pixels of the image. So I think the analogy of kind of putting these things on a cutting board, slicing them up, getting at that physics that actually builds these things up is appropriate. So let me start by laying a little bit of foundation for you for this talk, things that I think are worth knowing. Thanks to my PhD supervisor, I have a healthy appreciation of history and astronomy. So human beings have been looking at galaxies for many hundreds of years now and pondering their origins, going all the way back to the mid-18th to late 18th century with the works of people like Immanuel Kant. Somewhat characteristically, progress was much slower in those days. Understandably so, they didn't have the technology that we're blessed with at this day and age. But just to give you a sense of that, between the times of Immanuel Kant and Edwin Hubble in the early 20th century, we have a span there of almost 200 years. And in that time, most astronomers were really just trying to figure out what the heck these galaxies are that we see in telescopes, like people like Charles Messier were looking at. It wasn't at all clear that these things were actually outside of our own Milky Way. And it was Hubble's seminal work on the Cepheid variables in M31 that finally sealed the deal, and we figured out that galaxies are external to our Milky Way, separated by large distances of space. So,
you know, since those early days, we've been studying galaxies ever since. Over the last 10 to 15 years, I would say there's been quite a feverish pace in this research. Somewhat paradoxically, asking the question of what a galaxy is maybe a little bit profound. Chiefly, there's been discoveries of really faint galaxies in our own backyard, in the halo of the Milky Way, that make us question, you know, what do we think galaxies are? But my definition, kind of working definition, is that galaxies are huge accumulations of gas, dust, stars, planetary systems, and dark matter. And a lot of those elements, those ingredients, are visible in this gorgeous three-color composite image of the Andromeda Galaxy. This was taken with CFHT by a colleague of mine at Queen's University. We're sort of, I guess, research brothers. One of the other things to appreciate from this image is the rich amount of structure that we see within galaxies, you know, covering a wide range of scales. So in Andromeda, we see that it has a central spherical bulge made up of mostly old stars. It's surrounded by a disk of gas and younger stars, and then those two things are surrounded themselves by a halo that has a diffuse stellar component as well as globular clusters. In that disk, you could have things like spiral arms, bar in the center. So there's lots of really cool things for people like myself to gush over and think about. You know, what are these things? What's the role of these structures in the formation, or how do they even come to be when the galaxy is forming? Of course, when we look in the local universe, not all galaxies look like Andromeda. There's many different types of morphologies and visual appearances when we look at galaxies. So Andromeda and the Milky Way, they would slot in over here on the right-hand side of the diagram. This is populated by so-called spiral galaxies. And there's different subclasses of spiral galaxies. Andromeda and Milky Way would probably be right around the middle here. The boring, if you will, counterpart to spiral galaxies are the ellipticals and lenticular systems. These are just kind of like pure bulges, and they're passively evolving. They don't have cold gas to form new stars. So, you know, not much really to get excited about, I suppose, when you compare it to a beautiful spiral galaxy. And then you'll also find examples of mergers in the nearby universe. All that research that astronomers have been doing over the past decade or so has led us to realize that there are systematic variations of galaxy properties throughout this tuning fork diagram. Things like the size of a galaxy or the motions of its stars. Those change with the morphology of the galaxy, and we think that that is a direct result of very different formation histories for, say, the things on the left versus the things on the right. So we want to get at those details. What is that physics? And I think a neat way to appreciate just how different of a physical mixture you get in forming galaxies is appreciated by looking at the extremes of the end products. So at the very massive end of galaxy population, we have galaxies like M87, found in the center of the Virgo cluster. We think galaxies like this formed very early on in the universe, soon after the Big Bang. There's still accreting stuff at this day, but the bulk of the mass was accumulated within the first few billion years. And they've had things like mergers and supermassive black hole activity. You can see that actually going on in M87 here. And you contrast that with something which is about 10,000 times or 1,000 times smaller. This here is a recent discovery in the field. It's what's called an ultra-faint dwarf. It was discovered by the Dark Energy Survey. And just like the name suggests, these things are really devoid of stars. Very dark matter dominated systems. You know, you might get about 1,000 stars compared to 10 billion or so in M87 there. So interestingly enough, we think these things probably started forming very early on in the universe as well, but a dramatic event must have happened to get rid of all the gas in this system and didn't leave it any fuel to form any new stars. So vastly different physics going on throughout the spectrum of galaxy types that we see. But in addition to what we find within galaxies themselves, their visual appearances, their components. We also have to consider the environment in which we find galaxies. So if we go out and, recently as a result of the Solar and Digital Sky Survey, they were able to successfully map the positions of galaxies within about 2 billion light years of our position. And what they found was what you see here, and there's quite a different range of environments in which galaxies inhabit. We find galaxies in these really dense filaments, like you see here. At the intersection of those filaments, you'll find big clusters of galaxies. So we're talking about groupings of thousands of galaxies at a time. Then there's galaxy groups. Those contain about 10 to 100 galaxies. And you can also find large voids in the galaxy distribution, but there are still galaxies there, so they're evolving in relative isolation. Why the environment matters is because you have things like interactions between galaxies that excite gravitational interactions, and that can have a pretty big, a pretty large impact on the evolution of the galaxy itself. So that needs to be considered. Okay, what are the underpinnings for understanding galaxy formation? We set our theories of galaxy formation based on what's called the lambda CDM paradigm. Lambda CDM stands for dark energy, that's the lambda. CDM is cold dark matter. And the paradigm is referred to as that because it says that the matter energy density of the universe is overwhelmingly dominated by these two components. The stuff that makes up you and I is a very, very small fraction. And what I'd like to show you is a quick movie that shows us what a universe like lambda CDM looks like at the present day. So what you're looking at here is the zoom in of a very impressive simulation that happened actually about a decade ago, which shows the distribution of dark matter in the present day universe, so 14 billion years after the Big Bang. What you're seeing is the density of dark matter particles, yellow representing regions of high density, these black and purple regions are low density. What we're coming into here would be something like a supercluster of galaxies. So you can see that there is a wide range of structures that forms with the dark matter. So we get at the very large end are the superclusters. But as we're coming into this supercluster, you can see these little peaks, these local peaks in dark matter distribution. These are individual halos of dark matter. And why all this is important is because in this paradigm, dark matter represents like a flower pot, if you will, out of which the flower being, or the galaxy being a flower, the galaxy pops out of these dark matter halos. So they set the gravitational basin for the basis of galaxy formation. And one of the signatures of this lambda CDM paradigm is that the structures form hierarchically. So what that means is they form from bottom up. The smallest stuff forms first, the largest stuff forms later on. So this kind of supercluster here would have formed after many billion years of cosmic evolution. The smaller stuff formed first. And that, because of the connection between galaxies and dark matter halos, this kind of simulation has some important implications for how you go about forming galaxies. So with lambda CDM as our kind of baseline, what does a rough sketch of galaxy formation look like? This is a picture from the WMAP team, which tries to convey in the simplest possible terms the history of the universe. Here on the left-hand side, we have the Big Bang. On the right-hand side, we have the present day. So shortly after the Big Bang, you have very interesting events like inflation, the Big Bang nucleosynthesis, when the when the photons and the baryons decouple, you have the formation of the cosmic microwave background, and that's the point at which then the galaxy formation starts taking off, and you get the formation of the dark matter halos. Once those halos are gravitationally collapsing on themselves and get bound, then you have gas flowing into those halos. The gas cools and it settles into the center, starts forming stars. First stars pop up around 400 million years after the start of the Big Bang, so things are getting underway very quickly. And then you have this buildup, the mergers of dark matter halos and accretion of material, and that's how the galaxies begin forming. They start out as proto-galaxies and build into bigger things. From the less than 1 billion years after the start of the universe, we had the first galaxies popping up, and then they're growing over time until the present day. Interestingly enough, we've learned that the biggest galaxies in the universe, those big ellipticals like M87, they really formed, within that few billion year slice, and the other galaxies like Andromeda, the Milky Way, and dwarf galaxies, their formation histories are more prolonged. So that's just a really basic sketch of what galaxy formation looks like. There's a lot of details left for us to figure out, things like reionization. So at very early times in the universe, the gas that permeated the intergalactic medium was largely neutral. At some point, we had either stars or quasars popping into existence. Those things ionized all that gas, and that probably changed the lives of dwarf galaxies pretty severely. Supermassive black holes, we look at massive galaxies in the nearby universe, we find that they have these really massive black holes, like 1 million suns worth of mass in them. It's a real puzzle how you get those things to even form and grow. Star formation, we don't really know as much as we would like to. Star formation is one of the defining aspects of galaxy formation. And it can impact the formation of the galaxies pretty importantly. How that star formation permeates through time, the history of star formation, is really interesting. The ways in which galaxies gain material, do they come in through mergers, or are they coming in smooth trickles of gas? We really want to break that down. And then feedback. So the explosions of massive stars, the accretion of gas on the supermassive black holes, these are events that release a lot of energy into a galaxy's gas component and can dramatically alter what happens in a galaxy afterwards. So there's lots of stuff for us to be thinking about and that we're still working on. And that means we all have our favorite tool that we like to apply to galaxies to understand, to get ahead of all these problems. And my particular set of tools focuses on the stars within galaxies. And the reason I like studying stars and galaxies is because they act kind of like a time capsule. So when we record light from stars, like the sun, we can get something that looks like this. This is just a representative slice of the sun's spectrum. This is like around green wavelengths. And you see that the spectrum is marked by all these absorption features here. And when we study those absorption features, or stellar astrophysicists study them, they can recover things like the surface temperature of the star, its gravity, its chemistry, really important parameters regarding a star. When we look at galaxies, though, in the nearby universe, we don't often see individual stars. I mean, in very nearby galaxies, yes, we can look at individual stars, but it's not often. And when we look at galaxies, and specifically when we look at where galaxies are forming stars, like M83 here, this is a nice image taken with HSD. Looking at the inner regions of the galaxy, there's the center, this is a spiral arm coming out. And we see these red regions along the spiral arm. These are locations where new stars are being formed. And the red indicates emission from hydrogen gas. The hydrogen gas is being excited by these new stars. And there's just no way that these individual regions are being excited by individual stars. No, in fact, we have clusters of stars being formed. And really and truly, that's how we think stars form in galaxies. They form in these clustered arrangements. But over time, those clusters disperse into the field stars, like what you see in this region down here. So that's kind of the broad brush way in which stars form. Clusters then disperse into the general field. But that point about, the clustered nature of star formation is kind of important because we can learn some interesting things from clusters of stars. So here's a typical cluster, globular cluster that we find orbiting our own galaxy, 47 Canis. And if we were to take the stars from this cluster and we measure their brightnesses and their colors, we plot them in this kind of diagram of brightness. I have temperature here, but think of this as color, with blue things being on the left, red things on the right. We see that the members of this cluster form this really tight sequence in this space. And this is actually representing a mass sequence for the stars. So up here are the higher mass stars in the cluster, down here are the lower mass stars. But why is that important? Well, that sequence, what we call the main sequence of stellar evolution, behaves very predictably as a function of the age of the cluster or its chemical composition. So here you get an appreciation for the age effects. So this is that same diagram, brightness versus color. And when we go to our computers and we compute models of stars and clusters, sorry, more specifically clusters, and we let that cluster age, this is what happens. It starts out with the brightest stars being very blue, so overall the cluster itself is very blue. Then those very massive stars, they burn through the nuclear fuel very quickly, they evolve off that main sequence. So that top of that main sequence peels off down here towards redder colors or cooler temperatures. And so we have this very predictable age effect on that main sequence. Okay, and we have similar effects with things like chemistry. So when we look at stars and galaxies, when we measure the spectrum of a galaxy, or we measure colors of galaxies, we can actually invert those measurements into constraining things like the ages of the stars within galaxies, their chemistries, and their masses. And so this is my the object of my research is to infer these kinds of quantities based on data that is given. Okay, so now I'd like to shift a little bit of the focus. Let's get into more of the specifics for the project that I'm doing at HIA. And I'd like to just motivate that project on two grounds. The first is that since the early 2000s, those of us in the extragalactic community are now living in kind of a golden age where large galaxy surveys are becoming increasingly the norm. And that was more or less started by this thing called the Sloan Digital Sky Survey. And here's a big picture of the telescope that was powering that survey. One of the Sloan's crowning achievements was that it measured distances to 1 million galaxies, but it also did a lot more than that. It actually fed my thesis, and I'm sure many other students' thesis. An incredible amount of literature was gained from this survey, delivering imaging and spectroscopy for galaxies. So this really changed the game for those of us interested in galaxies, because we can get large samples of galaxies. We can start doing statistics on galaxies. Now we're entering kind of another new age in the research on galaxies, and that again is being powered by that Sloan telescope or the Sloan Foundation. So we have even more to be grateful from the good people there. One of the chief differences now is that in that first era of large galaxy surveys, we were looking at just a single part of a galaxy, like its very central regions, or we were looking at the whole galaxy at once, like the integrated light. Now, we're starting to look at the different parts of a much larger area within galaxies. And this is thanks in part to technological improvements, which allow us to place these bundles of optical fibers onto galaxies in the focal plane of the telescope. And then we can actually record the light as a function of position within galaxies. Those fibers send light to spectrographs, which then split the light by through like a prism into the constituent wavelengths. So now we can actually get spectra as a function of position within galaxies. And that's really important because spectra are incredibly rich data sets to work with. We can get a lot a lot of useful quantities on galaxies from spectra. So now we're entering into this era where we're studying whole regions of galaxies. We're studying galaxies in 2D. And so this is kind of what these new surveys, these two-dimensional spectroscopic surveys, or IFU surveys, kind of look like. You can see this pattern, you can appreciate the regions now that we're monitoring within galaxies. And because we're getting spectra within these broad areas, we can measure the motions of stars and gas. We can trace the buildup of different galaxy components like the disks and the bulges. We can look at the chemical enrichment of the gas and the stars in the galaxy. And we can also get a handle on the dark matter. So it's you get a lot of bang for your buck in this. And I should mention is that these surveys, I mean, it used to be that you could get with these IFU instrumentation, you can get a few galaxies in a given night or over several observing nights. Now we're doing 10,000 galaxies. So it's quite a leap forward. Okay, so that's the first thing. We're studying galaxies spatially. Second thing is it's quite a challenge to study the populations of large populations of galaxies covering wide ranges in their properties, like luminosity and size. And the reason for that is because there's an inherent bias built into where we find galaxies. So the example of that is the very faint dwarf galaxies that we find within our immediate backyard of the universe. So this is a plot of the 3D distribution of galaxies in the local group. You have the Milky Way here, M31, Magellan Clouds, and most of these other dots are these really faint dwarf galaxies. And because they're faint, we're biased to finding them in this immediate volume that we inhabit. Contrary to that, if we want to look for elliptical galaxies, we have to move outside of our local group to different environments. So, probably one of the closest elliptical galaxies is Maffei over here, which exists within a different group environment. So, it's inherently challenging to study galaxies over wide regions of their parameter space all at once. But we can hope to make some progress on this by looking at rich galaxy environments. So if we expand our volume around our location in the universe, look at about 300 million light years or so, we come across this thing over here, which is known as the Virgo cluster. It is the richest concentration of galaxies within this volume. And we know it already has very bright galaxies in it. It's very plausible that it has very faint galaxies in it as well. The trouble is, our existing knowledge of the Virgo cluster, the galaxy population within the Virgo cluster is very limited at this point in time. So people were wise to the Virgo cluster very early on. And back in the 80s, there was a push to survey the galaxy contents of this cluster with photographic plates. And this here is just a plot of the number density of galaxies within that cluster as a function of their brightness. So you have bright things over here, faint things over here. And you can see that all these curves refer to different morphologies of galaxies. So Virgo is very rich. It has basically all the galaxy types that we know of in the nearby universe. So we have spirals, we have ellipticals, lenticulars, and we have dwarfs. The problem is that the faintest galaxies that we find in the local group, they're over here. And that's where photographic plates can't get you any further. Okay, so there was this cutoff in our knowledge of the population of Virgo, right around the point actually where the local group dwarfs kick in. So because of that, that outdated information that we had on Virgo, there was a collaboration started a few years ago now. It's called the Next Generation Virgo Cluster Survey. This is led by staff at HIA, Laura Ferrese and Pat Cote. Some of you may be familiar with them. They sought to remap the Virgo cluster at optical wavelengths to really fill in the gaps of our knowledge of what is in Virgo. And what you see here is a plot of the Virgo cluster on the sky. And the rectangular-looking shape, that represents what was known from the 1980s based on photographic plates. The red circle represents the area surveyed by this NGBS. So it's surveying most of what was known about Virgo, so centered on the two main subclusters, M87 subcluster up here, M49 subcluster down there. So covering a wide range of area. The workforce instrument for this survey is the Canada-France Hawaii telescope on top of Mauna Kea in Hawaii. There's a nice picture of CFHT and the telescope within the dome. The instrument that was used was this MegaCam imager. It's an optical imager on the telescope. Very wide field of view, so it's comprised of almost 40 individual CCDs. You can appreciate the wide field of view here. This is the full moon. You can almost squeeze in 2 full moons worth of imaging in a single exposure. And just to appreciate the vast amount of data that's been collected as part of this survey. So this is a photo taken on top of Mauna Kea, looking at CFHT towards the easterly direction. And this here is a mosaic of all the imaging that's come from the Virgo clusters, from the NGBS on the sky. This is my shoddy attempt at drawing the Virgo constellation. But it's just a wonderful survey. Just to appreciate that the survey is achieving its aims. So I mentioned that the survey was really going after the faint galaxies in Virgo, or just faint anything in Virgo. So one of the faint things is galaxies. This is a cutout from the NGBS survey, so we're looking right in the heart of the Virgo cluster. This is M87 right here. You have the Markarian chain up here. And zooming in on this small little region, you can see that they've uncovered a smudge of emission. That smudge is one of the many new galaxies that's been detected by the survey. So this is obviously a very faint dwarf galaxy in the Virgo cluster. And it's just really nice to contrast the brightness of this thing with previous galaxy detections in this cluster. These are the photographic plate galaxies outlined in yellow. So it's just a startling improvement in sensitivity as a result of the survey. So the survey isn't just limited to finding dwarf galaxies. We can also look at big galaxies like M91. Here's a nice 3-color image from the survey. And in addition to the disk and the bulge of this galaxy, you can see that there's a really nice halo of stars that's popping out from the survey data. If we zoom in on one segment of that galaxy, you can see that we're finding things like globular clusters, background galaxies, even foreground stars in the survey. So there's really exquisite resolution in these images. So there's just a beautiful imaging data set that the NGBS is obtained. Now, just to drive home that point of how we're uncovering gads of new galaxies in the Virgo cluster, here this is a plot of the brightness of galaxies as a function of their distance from us. And data are being shown here from 3 large surveys of galaxies. So each individual point represents a galaxy. All the stuff from the NGBS is at a particular distance from us. That's because it's within a cluster, so it's basically all lying at that single distance from where we are. What I hope you can appreciate is what's happening down here. Okay, all the other surveys are limited to galaxies of brightnesses that are 5 order or 100 times brighter than what the NGBS is pushing down to. And if we want to find any other galaxies like this, we're basically limited to the local group, or we're just a little bit beyond that. So we are finding analogs to the dwarf galaxies of the local group in Virgo now. So that's really impressive. Now, when I got involved with the NGBS, I got really excited based on the quality of the imaging that was being obtained, and having a bit of foresight to what was coming up in the field, we realized that the NGBS would be a great place to do this kind of dissection experiment that I talked about at the very beginning of the presentation. Albeit we're doing this with imaging, we're not doing it with spectroscopy, but it's very simple for us to break the galaxies in the survey up into individual pixels and look at the stars within those individual pixels and measure useful properties for them. And what I'm most interested in is measuring their masses. So the project that I'm leading within the NGBS is to map the distribution of stellar mass within these galaxies. And the aim there is to unveil a new side of galaxies, which is their mass side. We've spent a long time looking at them just in terms of light. We need to start looking at them in terms of mass. And this is, of course, appreciated by many other people working in the field, and many other people are trying to do very similar things. So this is an example of the kind of experiments that are being done with those large 2D spectroscopic surveys of galaxies. Here you have some images of galaxies from the Khalifa survey, and these here are maps of the stellar mass within these galaxies that are being constructed. So what you're looking at is basically the density of stars within individual fiber bundles within these surveys. So one of the advantages we have with NGBS, though, is that we can push our maps of the stellar mass within galaxies to larger radii than what you can do with spectra. There's just more signal in images of galaxies rather than their spectra. And then we also can have better resolution. So there's a really nice complement to the NGBS studies that we're leading. What do we ultimately want to do with this? I mean, it's a very nice exercise to map stellar mass within galaxies, but what is the fundamental science that we want to achieve? Having maps of stellar mass for galaxies will allow us to trace things like the structure and the growth of the galaxy components, like their bulges and disks. We know that if we break galaxies up, pixel by pixel, and map stellar mass within the individual pixels, and we add all those values up, we're going to get very accurate very accurate masses for the stars within the whole galaxy. And knowing what we know about the importance of stellar mass for galaxies, that's a crucial aim for this type of work. And if we can get kinematic measurements for some of the galaxies in our survey, we can also use these mass maps to unveil the dark matter halos that these galaxies inhabit. Okay, so let me spend the last few slides of the talk just showing a few preliminary results from the work that I'm doing with the NGBS. So what I've done is I've gone through the very central region of the NGBS survey, and I've picked out a few representative types of galaxies. So we have a nice interacting galaxy here from the Markarian chain, spiral, elliptical, and a small dwarf galaxy. And what I hope to convey to you through a comparison of the light versus the mass in these galaxies is that when we're looking at the mass in galaxies, we're really seeing galaxies in a new, dramatic way. So here's the elliptical galaxy that I spoke of. Nothing too remarkable about it, except in the very center of the galaxy, we have a prominent dust ring. So maybe this galaxy in recent history has had a merger, like a satellite galaxy fell into it and ignited some star formation in the center of that galaxy. When we map the mass of the individual pixels in this galaxy, though, we see that there's nothing dramatic at all in the center of that galaxy anymore. It's just a smooth structure. So whatever that dust was hiding from us in the light, it's nothing too remarkable happening behind that dust. Here's that dwarf galaxy. The dwarf galaxy is interesting because it has this strong concentration of blue light in its center, which indicates that this dwarf recently had a major star formation event in its center. Yet, when we look at the mass, it's pretty uniformly distributed. So whatever is going on here, it doesn't actually represent a huge contribution to the overall growth of the galaxy. It's kind of just a flash in the pan, if you will. Spiral galaxies are really interesting to look at in terms of light versus mass. Spiral galaxies, like M31 that we saw at the start of the talk, lots of structure in them. You got the spiral arms here, dust lane in the outskirts, bar. There's also all these blue dots represent sites of recent star formation. So you might, if you were to try and analyze the structure of this galaxy just based on the light alone, first of all, it'd be very difficult to try and deal with these non-axisymmetric features. Yet, if we look at things in terms of stellar mass, it's completely smooth. Nothing remarkable happening behind that dust. The stars that are being created in the spiral arms, it's just a small fraction of the mass. And that bar, you don't really notice it too much. So the structure of galaxies is really smooth, inherently smooth in terms of mass. And we're really biasing ourselves when we're looking at the light in galaxies and making inferences based on that. This is that interacting galaxy. So this was probably a spiral galaxy. A little bit in the past, came into the presence of this elliptical galaxy over here, and the elliptical is driving all sorts of tidal features in this galaxy, drawing out these long arms of gas and newly formed stars. So you see the blue light indicating new stars over here as well. Lots of dust happening in the center of the galaxy, also probably some star formation there. Yeah, when we look at the mass, it just blends right into the background. So mass is really giving us or looking at galaxies in terms of mass is really changing our perceptions of galaxies. So just to summarize, start of the talk, galaxies are really rich, interesting systems to study. Lots of different physics that we need to consider, so we need to really kind of partition things based on mass or light and look at things individually. We're starting now to study the spatial variations of properties within galaxies, not just the stars, but looking at the motions of the gas in stars, looking at the chemistry within galaxies as a function of position. This is where the field is really moving, and we move with that field with the NGBS. So now we're starting to make our own contribution to that development, starting to look at the mass distributions within galaxies. Very excited to see what shakes loose from this area, especially since we have this new parameter space within that vertical cluster where we have all these really faint dwarfs that we can play with. So the future looks pretty exciting, and I thank you for your time.
Boy, I have lots of time for questions. So who has some? Who's the first one? Gary.
First of all, may I say how lucky you are to be smart enough to be studying these things. It was fascinating stuff. I'm just so jealous.
And to get paid for it too. That's the most important part.
I have a question about why do spiral arms form in the first place?
Those are density perturbations within the galaxy disk. There's still, I think, some debate about what sets up the density wave within it, but you can think of it as it's a propagating wave of increased density throughout the galaxy. But that's not my own area of research, so but I do know that it's still kind of debated what sets these things up.
How about the bars at the center of something else?
Those are similar to spiral arms. They're a perturbation within the gravitational potential of the galaxy. They're just kind of a different mode, if you will, of they don't have trying thinking way too much. They're just a simpler version of a spiral arm. So you can just have like these if there's enough, if the disk of a galaxy is cold enough, then they become inherently unstable to forming these kinds of structures. That's one theory, anyways.
Lori.
Let John go first.
Go ahead, Lori.
Okay. You mentioned at one of the earlier slides that there were the stars are being formed like us, for instance, in the spiral galaxies. In the blue areas you were talking about, that's where the new stars are being formed, and then you mentioned that they disperse to go into the into other areas where we don't see them. How do they disperse? I mean, are the actual stars moving into those spaces, and how do they move and what makes them move?
Yeah, so within the clusters themselves, once you lose mass from a star cluster, then you eventually just kind of evaporate. Stars just kind of move away from the cluster, and that is the internal motions of the stars within that cluster plays a role. So that is a well understood phenomenon. Then then stars can actually move around within galaxies, and things like spiral arms are excellent distributors of stars throughout galaxies. So they can have a transfer of angular momentum with a star. So when you have a star within the very center of the galaxy, it has a very low angular momentum. It can gain angular momentum from the spiral arms and then move to a much larger radius, say, within the galaxy. So there's actually some really interesting surveys that are ongoing within our own galaxy that are trying to identify exactly how stars kind of permeate throughout galaxies over time. And these are like, the Australians are really heavy into this, trying to find groups of stars that form together based on similar chemistries. So it's really interesting what we'll see coming out of that.
So what is our star then?
Our star, it may have formed closer into the galaxy and actually moved out over time. We know that our star may be just a little more metal rich than we would have expected based on what we see within our own solar neighborhood. John?
Yeah, I'm interested in the business of galaxy evolution over time. And I think you mentioned that a lot of the big elliptical galaxies formed early.
Mm-hmm.
Are spiral galaxies going to evolve toward elliptical shapes over time, or is that no? With more mergers and whatnot.
Yeah, I would say that at this day and age, a lot of spiral galaxies will stay spirals. The number of mergers that's happening in the present day universe is quite a bit lower than what happened.
So you need a lot of mergers to get the ellipticals.
Not necessarily. In fact, what we've been seeing at high redshift is that most galaxies, it seems, started off in a kind of disky form. That's just the nature of angular momentum conservation as gas pools. But what happened to a lot of galaxies at high redshift was they became gravitationally unstable. They developed really big accumulations of gas and stars. It was almost like you can imagine a disk rotating, and then all of a sudden these huge, like an analogy is like a bowling ball of material just forming, and then these things spiral into the center of the galaxy and start to form like a bulge. And it's plausible that some elliptical galaxies could have formed through this kind of disk instability. So you don't necessarily need mergers, and there's kind of an overlap actually with that picture I just described with the kind of merger. I mean, at least in terms of what you would predict the end product to look like. So, yeah.
Thanks.
That's
When I see pictures of dark matter halos, and including the ones that you've shown, the impression I get is that the dark matter halos around ellipticals are actually very similar in shape to those that are around spirals. Is that a false impression, or is that basically true? And the follow-up question from that then is, well, how do the spirals and the elliptical galaxies form so differently if the dominant gravitational forces are from the dark matter, which have similar forms?
Mm-hmm. That's a really good question. First off, it's, I hope I didn't give the impression that we can see dark matter, because of course we can't see, we infer it, yeah. But that's a whole independent area of research, is actually studying the shapes of dark matter halos. Friends I went to school with actually did that sort of thing. I would say that, it's dark matter and gravity aren't the only, physics that drives galaxy formation. And like I was saying earlier, that the small scale physics we know is really important in galaxies. So like the feedback that you get from supernova explosions or supermassive black holes, those can be very transformative to a galaxy. So there is a whole lot of sort of other ways you can have a spiral galaxy differentiated from an elliptical. Just a simple example that I could think of would be a merger. A spiral galaxy that didn't have a merger, a spiral galaxy that did have a merger, and that one over here winds up as an elliptical, and yet they still have similar dark matter kind of shapes.
So, you're talking about the formation of galaxies, and so many have these massive black holes in the center. Were you also saying then that it looks like dark matter maybe is what's driving the formation of those black holes? Drawing everything in, the mass of the dark matter, and then the black holes forming from that, or something else?
Yeah, on some level, so from what I've gathered about the people that study black holes, is the real trouble understanding them is you needed some kind of a seed black hole, and it's not clear if these things could have just formed primordially, like you just get a huge amount of kind of matter that just collapses onto itself, or are these descendants of the first stars? So dark matter definitely kind of plays a role in all that, because it is concentrating the matter together, it's bringing everything together that you need to make a black hole. I don't know if it fundamentally, other than just being that kind of potential, that well, other than that it has anything to do with it.
How much of your time is spent on your research? Are you using current observations as opposed to going through databases of previous observations?
So my PhD was based on Sloan, or leaned heavily on it, and the stuff that I'm currently doing, I don't know. I think NGBS has maybe kind of hit that sort of stage of being a database at this point. Even Sloan now is still producing papers, so it's there's no amount of limit to it seems to what you get from these databases. But then at the same time, I have other research projects that I'm involved with that's actually actively taking data on telescopes. So I'd say right now I'm very heavily invested in NGBS, so like 80% of my time, I'd say, is on that, and if you want to call that a database or and then the rest would be spent on these new observations.
Okay, thank you very much, Joe.
Thanks, Joe.
And there's a water bottle.
Oh, great. Thank you so much.
Okay.
Love it.
Thanks.